Good morning. We will continue factor analysis, that is the third lecture on factor analysis. In first lecture we have described the conceptual model and we have given some examples, and in second lecture we discussed about the model estimations, that is from principal component analysis point of view, from principal factor method point of view, and also we have discussed discussed about the maximum likelihood method point of view. This lecture will start with model adequacy test. Model adequacy test, then followed by your factor rotation, followed by factor scores, then I will show you SPSS exploratory factor analysis, and if time permits I will go for confirmatory factor analysis. That only basics. So, under model adequacy test I have already discussed the correlation matrix, and I said that if there are substantial correlation coefficients greater than equal to 0.30, then you go for factor analysis. Means suppose you have a large data matrix and the correlation coefficient matrix is P cross P, there are large number of values having more than 0.3. Second is Bartlett-Felicity test. Bartlett-Felicity test uses this formulation, that you find out the correlation matrix first, take the determinant of it and take logarithm of this, then you multiply with this, this ultimately follows chi-square distributions with p into p minus 1 by 2 degrees of freedom. Now, if this quantity is more than the tabulated value, then the null hypothesis that no factorization possible, that factor analysis is not possible, that is not true here. Okay. So, we will reject null hypothesis in this case. Then another one is that large sample test, which is likelihood ratio test, large sample likelihood ratio test. So, we will again give you the Bartlett procedure here. Here the null hypothesis is that the population covariance matrix is coming from the factor model. I mean, we are able to reproduce from the factor model this population covariance matrix. It is correct. And H1 is that sigma is any other positive definite matrix. Okay. So, this is my step 1, that means set the hypothesis. Your step 2, you have to find out the statistics, appropriate state statistics. What is your state statistics? As I told you that it is the log likelihood ratio. So, minus 2 log this capital lambda, this lambda is not this capital lambda. So, in this case this is basically similar to this Wilks lambda what you have seen earlier, that similar to that Wilks lambda type of things. So, if I write like the not lambda here, if I write that this is our, let it be W. So, we are creating this, and that one is minus 2 log log determinant of that sigma cap by determinant of Sn, where Sn is n minus 1 by n into S, that is the sample covariance matrix. For n greater than very large tends to infinity, then Sn become S. So, for large sample size you can use S determinant here, determinant of S. Okay. Then once I know, so that means what is my state statistics here? My state statistics is minus 2 log determinant of sigma by determinant of Sn. Then you have to find out that what is the sampling distribution of the state statistics. Now, Bartlett says that m log determinant of sigma by Sn. So, please keep in mind that we are writing the estimate value here sigma. This one, because this is what is our random variable, random component here. So, this follows chi-square distribution with half of p minus m square minus p plus m, that degrees of freedom. So, first this hypothesis related to the population, then sample statistics related to the estimates, then your sampling distribution related to the estimate. Now, you have to take the decision. Decision will be reject H0 if this quantity, if I write this total quantity as D, so if D greater than equal to chi square half p minus 1 square minus p plus m, that alpha, for maybe usually alpha we take 0.0. So, if you reject H0 for this condition, what does it mean? You are saying no, it is not, that the factor model is not able to reproduce the population covariance matrix. So, if you want to have your factor model acceptable, then H0 should be accepted. Okay. So, this is from the hypothesis testing point of view, correlation matrix, Bartlett test, all those things we have discussed. So, next issue is that number of factors to be written. How many factors you will keep? So, it is similar to principal component analysis, where we have seen that number of component to be kept by several means. For example, percentage cumulative variance explained, then we have also given you eigenvalue criteria. So, how much? It may be eigenvalue criteria when you use R matrix, then scree plot is there, similar things. Okay, similar many things we have explained there. For example, let we have p variables, you have extracted, let it be 3 factors, and you know the loadings. Okay. If I say, then you know the eigenvalues here. This is 2j, 3j, 3j, j equal to 1 to p, that square. So, you find out the percentage, what percentage it is, what percentage it is, what percentage it is. Then you find out the cumulative percentage. Set a criterion, let you want the cumulative percentage, it should be greater than equal to 90%. Are these three factors you are considering able to explain this? If yes, this factor model is good and you can keep three factors. Okay. Now, scree plot also you have seen earlier. Your scree plot, what we have seen, that this eigenvalues vis-a-vis factor 1, factor 2 like this, eigenvalues, suppose your values are coming like this. So, this is your elbow, so you keep three factors. An eigenvalue when you use R matrix, so for those eigenvalues which are more than 1, that you consider at least 1, and at least one variability will be explained by this. Okay. This is similar to principal component analysis, how to keep the how many components you want to keep. Okay. As we have discussed earlier, factor analysis has two important purposes. What are those two? One is your definitely dimension reduction, second one is interpretability. By interpretability we want to mean that we will be able to provide name to each of the factors. Correct. So, how do you provide name? For example, consider that we have three factors here and there are several variables like this, and when you have seen the loadings, that means lambda values, you might have found out a situation similar to this, where these loadings are high with factor 1, these loadings are high with factor 2, these loadings are high with factor 3. But the other loadings like x1, x2, x3 loadings on factor 2 as well as factor 3, they are very small, negligible. That means we can ignore those loadings. Under such situation, what we can say that x1, x2, x3 is creating factor 1, x4, x5 is creating factor 2, x6, x7, x8 is creating factor 3. Then we can probably name these factors considering what are these variables, what is the nature of these variables. The name will be governed through these three for F1, these two for F2, these three for F3. Can we get this structure? Immediately when we basically conduct exploratory factor analysis the way we have discussed. by any of the method, maybe your principal component analysis method, your principal factor method, your maximum likelihood method, any one of the method you have extracted factor, estimated the factors, parameters, models are available, are you getting this or not? It may so happen that you will not get this structure. Under such situation, it is desirable to rotate the factor in such a manner that the loading of some of the variables on a particular vector, that f1, that factor, that will be maximum, whereas the loading of other variables will be minimum. Similarly, we want to find out some other set of x excluding the ones we have considered for the f1, that which will be highly loaded with f2 and very low loading with other factors. So, this can be possible through factor rotation. Okay. So, in order to understand this fully, I will first show you one example. See, this is the results obtained by Maxwell and Lawley 1971 paper. They have conducted factor analysis of per responses of 220 students under 6 variables: Gaelic, English, history, arithmetic, algebra and geometry. And the factor loadings, they have extracted 2 factors, factor loadings and then commonalities are like this. Okay. Now, if you see these loadings, Gaelic is equally loaded, almost equally loaded with factor 1 and factor 2, because the loading value is 0.553 for factor 1, 0.429 for factor 2. Similarly, English also definitely English has certain higher loading on factor 1, little lower, but it is not negligible loading. For history, again equal pattern almost. For arithmetic, yes, there is higher loading for factor 1 and definitely from compared to 0.74, 0.27 is less, but none of the loadings here, if you find that, are 0. In that sense, none of the variables are not loaded with the 2 factors considered. Okay. Keep in mind that this negative symbol here given, this is not a issue here. Basically, it may be the negatively loaded or positively loaded, but they are loaded. Okay. So, under this condition, if we want to see the plot of these factor loadings, what we will see? You will see that your this basically for different factors, for example, factor 1 and factor 2, these are the 2 axes. Now, Gaelic 0.553 and 0.429. So, I think 553 somewhere this and 429 somewhere this one, this is the first one. Second, English 5.568 and 0.288, 0.568, 0.28 this value. Then third one is history 0.329, 0.329 and 0.450 is this value. And then arithmetic, algebra, geometry coming under this side. So, if we consider now these 2 axes, that first one, this one is f1 and f2, that what we have considered, then you find out that for these 3, arithmetic, algebra, geometry, almost highly loaded with factor 1 and lowly loaded with factor 2, but you cannot say that with the other that literature related things like Gaelic, English and history. They are almost at the here this side is okay, that are not highly loaded with the second factor or highly loaded with the first factor. So, under such situation, if I rotate the factor, can we get some better picture? So, if you rotate, you will get this type of picture. Okay, now let us see again this one, and I will draw that how it is possible. So, our case is like this. Case is like this. This is my F1 and this one is F2. Okay. Now, let us do some manipulation. What we can do, we will go for rigid rotation first. So, let us rotate both the axes like this. This is my new F1, then if I do perpendicular here, this is your new F2. I am saying this is star F1 star and F2 star, F1 star and F2 star. So, this one is rotated clockwise, so this angle is theta. Similarly, this angle is theta. So, if I know theta, then you will be able to find out F1 and F2 star from F1 and F2. Okay. And that is possible. For example, in this curve, suppose this is equal to 20 degree, then I think I have given you in principal component analysis one matrix like this T, which I say cos theta minus sin theta, then sin theta cos theta. That means what I want to say here, F1 transpose is your F1 cos theta minus F2 sin theta, and your F2 that new dimension is F1 sin theta, let it be plus F2 cos theta. Now, this plus minus symbol, this were the here or here, it all depend on the theta value. So, and we also have seen that this one, this T earlier, that if you say that T transpose equal to T transpose T equal to T inverse equal to I, then we say this is orthogonal transformation. Orthogonal transformation. That means, and we have done that because rigid rotation keeping 90 degree intact, we have done this one. Okay, orthogonal transformation. Using this transformation, you got this. Okay. You see now these loadings. Now, if I see the loadings from the arithmetic algebra geometry point of view, okay, this is the case. So, arithmetic algebra and geometry point of view, you see that in under factor 2, 0.001, 0.054, 0.083. almost 0 loading, but they are very highly loaded with factor 1, 0.789, 0.752 and 0.603 is factor 1. And related to factor 2, now at least what you are able to see that the first 3 variables, they are more, that they are higher loading, they have higher loading with factor 2 in comparison to factor 1. So, this is better picture. So, we can say now that these two factors are basically talking about two things, one related to arithmetic, algebra, geometry, which are basically mathematical ability, and other one Gaelic, English, history, these are all literature based. So, this may be your verbal ability. So, Lawley and Maxwell, they says that this intelligence, that having arithmetic, algebra and geometry, these are mathematical ability and verbal ability. These two component are factors are hidden there, and which are manifested in terms of the performance in the mathematical subjects as well as the literature based subjects. Okay. So, but here another issue is coming up, that issue is if we go for some other type of rotation which is not orthogonal, then what you will find out, suppose if I do the same, this axis, okay, let it be like this, but the other axis if I rotate like this, I will make this angle less than 90 degree. Then this will be known as oblique rotation. Oblique rotation. I mean there will be correlation between the two. There will be correlation between the two. Getting me? Now, what we can do, that we want to see under orthogonal transformation, or other way I can say under orthogonal rotation, are we losing anything related to explaining the variability of the original variables. Okay. Let us see this one. What is our covariant structure of the original variable? That is sigma, and we proved that this is nothing but lambda transpose plus psi. Okay. Now, if I create something like this, when we have created this type of transformation, rigid transformation, that f to your f to f star, that is f1 to f1 star, f2 to f2 star. Then what actually happened ultimately, our model is x minus mu, that we say lambda a plus this is our original model, and from this model you got this structure. Now, instead of this, if I say that f star is nothing but a, that is t and a, tf, because what you are doing here, you are writing f here with some other matrix, this t, f is tf, where t has having this property. Getting me? So, that means my model will change to x minus mu equal to lambda f star plus delta, some other directions. What will happen to this lambda star, sorry, lambda transpose? So, you will instead that it is basically lambda will become lambda f is there, so this lambda f will become lambda T f, fine. So, then what I can write, you can give some other symbol, then lambda T f, and this side it is coming lambda transpose, that will be F transpose, again T lambda, or lambda if we keep out, do not keep out, just if I say transpose here, F transpose, T transpose and lambda transpose. The resultant matrix, what will happen, this lambda lambda transpose, that will be like this, sigma will come lambda lambda transpose case, it will be lambda T T transpose lambda transpose plus psi. The resultant thing will come like this once you manipulate in this manner. Now, what is T T transpose or T transpose T? T transpose T equal to T T transpose equal to I, even the inverse also I. So, this is again lambda lambda transpose plus this. So, from covariance structure point of view, there is no problem, you are explaining the same structure, only thing is that your this factor values are changing from F to TF, some other dimension, the loadings are changing. So, that means factor loading will not reduce the explanation power, it will keep the same amount of information from the variance explanation point of view, but from interpretability point of view it improves. Then what are the different types of transformation possible? One is orthogonal, another one is oblique. Under orthogonal, the most commonly used is varimax rotation. There are other methods like equimax, quartimax, but varimax is more popular, and varimax basically tries to, suppose if my row wise I am putting the x variables and column wise I am keeping f1, f2 like even the factors, then the purpose of varimax is that it will try that x1 must be loaded with one of the factors. That means, suppose if x1 is loaded with this factor, let it be this, but all other cases it is 0. Similarly, if x2 loaded with f1, fine, all other cases will be 0, but the some other can be loaded here, all things will be 0. So, like this. So, that means it will allow some of the factor variables to be highly loaded with some of one factor, and then rest with other factor, rest with other factor, like this a clear structure is visible. So, that is the advantage, and that is what we want also. For varimax rotation, there are some formulas available, and these formulas you can go through any standard book, it is possible, you will be finding out those things. Okay. Once you have completed all those things, that means all those things means what I mean to say, you know your factor model, you know your number of factors, you are satisfied with that number, you have seen that the adequacy of the model is properly tested and they are adequate, your even but large sample test is also satisfactory, all those things. So, factor models now can be used for some other purposes also. What is the other purpose? Other purpose is, suppose if I go for orthogonal factor model, so whatever factor you are basically obtaining, they are independent each other. So, like principal component analysis, these factors like principal components can be treated in a subsequent regression analysis where this will be used as independent variables. In that case, what is required? You require to know what will be the values of all those variables. So, if you want to know the values of the factors obtained, these are known for every observations related to x, these are known as factor scores. So, pictorially what we can do, we can write like this, that you have collected n number of data points and you have x1, x2 to xp number of variable or manifest variables. For every one you have collected the data and you have created factors with this data set FM. You are interested to know that for my ith observation, what are the values of F1, F2 and Fm. For example, if I say this is I1, Fi1, Fi2 like this Fim, this is a I can say multivariate observation, ith multivariate observation on all the factors. But these observations are not direct, because you are observing directly this x and you are using factor model. This, then there is a engine, this is basically created through the factor model, factor model. This is observed, actually these are unobserved, but you are finding out these values using this. These are known as. So, for the first one then it will be F11, F12, F1m. For the second observation F21, F22, F2m, or like this. For the last observation Fn1, Fn2, Fnm. So, as a result you are having a data set cross n cross m, these are known as factor scores. Fine. Now, how do you get these factor scores? What are the methods available? If you see the factor model, x minus f equal to x minus mu equal to lambda f plus delta. What are the things unknown? Your unknown thing is this is also unknown, this is also unknown, this is also unknown. Only you know this side, again this one may be x bar. So, though it looks like a regression equation, but in regression equation you know y equal to beta x beta plus epsilon. So, there you are interested to find this one, this x was given, y was given, but it is not like this here. So, this structure is complicated. Now, finding out this factor scores, what I can say that Fi cap, it is a difficult one, but there are certain methods like weighted least square method is there. You can go by the, as it is regression like equation. So, regression methods you can use, and maximum likelihood methods are there also. So, several methods are there, and if you go through good books like Johnson and Wichen book, Applied Multivariate Statistical Analysis, these three discussions are given, that how to go for these factor scores. Okay. Then our, as I said that what we have computed, that means the adequacy part is over, factor rotation and factor scores and use of factor scores is like this. Then what I want to just add little more about the confirmatory factor analysis here. In explanatory factor analysis, you have m factors and there are p observed variables and you are linking each like this, and when it is orthogonal there is nothing like nothing, but when it is oblique there will be relationship between the factors. So, orthogonal and oblique. In confirmatory factor analysis will be similar, but with a very important difference. This difference is I know what are the factors linked with which variable. Getting me? So, essentially if I take only two factors with three variables, suppose that three factors with suppose x1, x2, x3, x4, x5, x6, x7, x8, x9. Okay. Then this is my lambda 1 1, lambda 2 1, this is my lambda 3 1, then this one is lambda 4 2, lambda 5 2, lambda 6 2, this will be lambda 7 3, then lambda 8 3, lambda 9 3. This is delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, delta 7, delta 8, delta 9. Correct. Now, if I want to write down the equation, you can write down like this: x1 minus mu 1 equal to what will be lambda 1 1 f1 plus delta 1. x2 minus mu 2, this will be lambda 2 1 f1 plus delta 2. x3 minus mu 3, lambda 3 1 f1 plus delta 3. Now, x4 minus mu 4 will be lambda 4 2 f2 plus delta 4. Okay, so let me do little manipulation here. This equal to, this is related to f1. Now f2, let it be related to f3. So what is happening here then? This x4 minus mu 4 is lambda 4 2 f2 plus delta 4. Similarly, x5 minus mu 5 will be lambda 5 2 f2 plus delta 5, x6 minus mu 6, x6 minus mu 6 equal to lambda 6 2 f2 plus delta 6. Then your x7 minus mu 7, x8 minus mu 8 and x9 minus mu 9 if you write, these all will come on here, that x7 minus mu 7 is lambda 7 3 f3 plus delta 7, then lambda 8 3 f3 plus delta 8, lambda 9 3 f3 plus delta 9. So, this is we are talking about under confirmatory factor analysis. So, as a result, if I see this in terms of matrix, what you will get? You will get x1 minus mu1, x2 minus mu2, 2, x9 minus mu9 this side. This side, that structure is very interesting. So, for see x1 minus mu1 for f1 you are getting. So, that means this is lambda f1, f2, f3 will be there. So, this one is your 9 cross 1, this will be 9 cross 3 and 3 cross 1 plus your delta will be delta 1, delta 2, so delta 9. This is the case. So, what I want x1 minus mu1 equal to lambda 1 delta. So, lambda 1 f1 is there, f1 is there here 1 1. What will happen? 0. Then lambda 2 1 0 0. So, similarly 0, I think how many things are there? 3 probably, 3 lambda 3 1 0 0. So, similarly finally last one also 0 0 lambda whatever is 9 3. You will be getting first 3 here 3 variable, then 0, second 3 variable will be getting here 0, third 3 this will be 0, here you will get some values. So, you are not getting all the lambda values because which is not required, that is the difference. That is the difference. And another important difference will be here that we want, particularly for confirmatory factor analysis, we want this also, the covariant structure will be there. So, that means this will be my phi 2 1, this is phi 3 2, this is phi 3 1. Phi 2 1, phi 3 1. This structure also we want to keep this. Okay. Now, then if I go by the factor analysis that x minus mu equal to lambda a plus delta, then what will happen? We found out finally that sigma is the covariance of x, which is ultimately expected value of x minus mu transpose. And then we ultimately what we have found out? We found out with for orthogonal case lambda transpose plus psi we found out, because in between there was an I. When we have created there is an I. So, that I is nothing but expected value of f transpose. Okay. Now, in confirmatory factor analysis, not only we are doing this type of that so many coefficients lambda loadings are 0, apart from that there is variability amongst the f. So, this will not become I, this is not I, rather this will be your phi. So, then what will happen? The covariant structure will be this phi this plus psi. So, confirmatory case, why it is? Because we are going for oblique factor. Okay. So, keep in mind that there is definite purpose here why we are going for oblique, because it is basically we want to measure these factors as well as their interrelationship. This interrelationship is of importance, is very important for all of us. Otherwise, there is no difference. Suppose if I go for exploratory factor analysis orthogonal, then this plus psi, and confirmatory factor analysis which are talking oblique, this phi, this plus psi. Phi is the correlation matrix for the factors. Okay. Now, with this I say that we can now prepare to see software. Let us see SPSS. Last class I have shown you SPSS, this class also. Let us see SPSS, that how SPSS can be used for factor analysis. Any question? If you have any queries, so we can discuss, but please keep in mind few things for factor analysis. What is factor? Factor is unobservable or hidden. We say these are the causes, can be estimated through manifest variable x. There are estimation methods, principal component method, principal factor method, maximum likelihood method. The covariance structure is this, where this is loading matrix, this is the specific variance, this is your original variance. You may go for S, and that also then you will estimate using one of the method. There are several tests. So, factor adequacy, keep in mind your factor rotation, factor scores, then types of model, exploratory, confirmatory. Okay. Now, let us see this one. I will take one data set straight away from here, and let this data set is like this. Okay. So, there are, suppose there are 1, 2, that 7 variables. I want to do factor analysis. So, in using SPSS, go to analyze, then I think under dimension reduction. So, go to analyze, then go to dimension reduction, then click factor. Then here it will be asking that what are the variables you want to consider. We want to consider D to CH, all variables. Okay. And then there are many other things like descriptive, that variable you may be interested, variable description, initial solution. You may be interested to know coefficient, standard, determinant, KMO and Bartlett test. KMO test is there, which is known as that Kaiser-Meyer, O stands for Olkin probably, that Oaklin, Kaiser-Meyer Oaklin test. So, that is fine. Then extraction, which method you want to use. We have discussed principal component, maximum likelihood, principal axis factoring. These three we have discussed. There are unweighted, general least square, many things are there. Let it be principal component. Then scree plot, you may be interested in covariance matrix. Now, what will be your extraction criteria based on eigenvalue greater than 1 or fixed number of factors. Okay. So, let it be eigenvalue greater than 1. So, what will happen? Let us see. Then rotation you want to know, yes, let there will be Varimax rotation. Then you go for scores, you want score, yes, you save as variable. If you want to know the vector score coefficient matrix, click here, and then there are several options how to deal the missing values, what is the display, that is possible. Okay. So, click OK. Now, descriptive statistics, mean standard deviation, then correlation matrix is given here. Now, see the correlation matrix first. There are many correlation coefficients which are greater than 0.3. Okay. Now, that Kaiser-Meyer-Oakland sample adequacy test, based on that approximate chi-square, that degree Bartlett test of ferricity, significance is 0. It simply says that this data set is factorable, and sampling adequacy test value is not rejecting null hypothesis. Yes, the data means it can be captured. Then the communalities, I think at this point in time you are very much able to explain what is communalities. So, extraction, then initial, raw and rescaled. Rescaled means with respect to standardized variables. Now, total variance explained. If you see here, ultimately these are you can go up to maximum 7 components, but first component's percentage variability explained is 47%, second component explaining 22%, the two in total they are able to explain 70% of total variability. And as we have seen, we have basically selected that we want the eigenvalue criteria of 1 or more using correlation matrix. So, that is why these two factors we are keeping here, and please remember we are using here basically the covariance matrix in the raw data, rescaled data, that is what is the correlation matrix. See here the values are like this, but here this values is 2.31 and 1.24. So, two-factor model is possible because 70% of variability of job stress component, if I can explain using 2 factors instead of 3 factors, it is not bad, we can go for that. Now, scree plot will tell you that where do you want to, I think that 3 factors will be better because LO is coming here. So, that means this is not 1, but it may be more than 0.7, because that Joliffe book I have found that he says that if we go for eigenvalue of 1 or more criteria, then what will happen ultimately, you will find out that many factors to be excluded. So, he suggested that go for 0.7, 0.7 is better. So, go for 0.7. So, that means 3 factors can be extracted here, and that will give you little better structure. Now, these are that component matrix, your raw component versus scale component, that loading factors is giving here, and your rotated component also given. First one is this one is your original case, this is your rotated case, and component transformation matrix using rotated factor. So, under rotated case KMU, Bartlett test, all those things are giving. Again it is repeated, and what is more important here, I think we have not taken this one, that the plot, this factor, that component plot we have not considered here, okay, but you can probably do. So, now I am going for 3 factors because we found out that 3 factors may be a better one. So, let us go to this extraction, I will write fixed number of factors, that is 3. Then okay, principal component let it be, then rotation let it be, loading plots, now I am giving loading plots, okay, rest I am keeping as it is. So, come to this, so what is happening here, your 81% of variability can be explained if you go for 3 factors. It is a better one, And now after that I will show you the component loading plot. Okay, 3 component at a time plots are giving, but it will be better if we go for 2 component at a time, that will be much better, visibility will be much better. Okay. So, I think in SPSS it is very easy to conduct factor analysis, provided you know the theory behind it, otherwise what you will get, you will not be able to interpret properly. Confirmatory factor analysis, there are for confirmatory factor analysis there are many other methods of estimating the model fit. What I can say, that model adequacy. What is the model adequacy that you want to estimate, that is possible through different methods, different index are developed, but there those things I will be discussed in structural equation modeling again, and which are equally applicable to confirmatory factor analysis. Thank you very much.